So it's tying all of this together, and what relates to this curve here isn't so much the raw engineering. It's the fact that it's sort of brought up to this level of technology where it's enabled us to do new things. And in particular, if you look at all of these technologies, Rich DeMillo, who is now head of a University for the 21st Century program, defines innovation as invention plus impact. If people don't use what you create, it's going to die, and it doesn't matter. So let's talk about some of those. And some of those may not be the things you might expect. So the person on the left is Mead-Conway. The person on the right is Carver Mead. Carver Mead is one of the reasons nobody will ever build Cray supercomputers like what you just saw. Nobody was ever going to, again, build giant boards with individual logic gates with a bunch of wires. People at the time thought that's the way to go. Bigger must be better, right? Carver Mead was one of the first people to figure out that when it comes to digital design, and those of you who are taking advanced computer engineering class know this, up to some sort of weird quantum level, things get easier as you get smaller. As you get smaller, you can use smaller voltages, get smaller gate capacitances. Things actually get better in computing as you get smaller. So no one's ever going to build a Cray 1 again. But their main contribution was to democratize integrated circuit design. Before Mead-Conway and Carver Mead got a hold of this, chips were designed by specialists in the device physics and the fabrication technologies used to make those chips. It was hugely expensive. They were able to extract what the fundamentals were to create some higher level design rules and create some software to do it. Most of you probably use Cadence or something crazy now. When I took VLSI design, we used a program called Magic, and it was free and it was clunky, but it worked. And all I remember is I think it was red, green, and yellow, I forget, and if you cross them in different combinations, you made transistors. But they were able to extract the rules of putting these things together that people who are not necessarily experts on the device physics could start designing chips. They were instrumental in founding an organization called MOSIS that would let universities go and actually fab chips as part of a bigger run. And so as a result, and people hated this. The people who designed chips thought, no, we are the high priesthood of device physics in our little industry lab. How dare you, mere plebeians, think you can design integrated circuits? They started a revolution. They took the engineering and raised it to the level of technology. Here's one you probably don't know about. This guy on the left is Philip Kahn. You assume now you have all of these amazing free compilers. GCC this, GCC that, all this whole open source movement. But in the early 80s, compilers were hugely expensive. And they also sucked. They were super slow. Philip Kahn comes along and says, let's just make a few basic tweaks. Puts out Turbo Pascal. It's faster than any of Microsoft's products. And more to the point, he sold it for $50. That meant that my parents could afford it when I was, about to go to college. It meant that every university started teaching Pascal, which Pascal was designed as a teaching language. But what cemented it was the fact that there was this really competitive compiler that this guy had the tenacities to sell for just $50. It's $50 and it was better. And I'm told that Bill Gates would periodically go and chew out his compiler team. How is it that this guy, his company, is coming up with a cheaper product that actually is way faster and way better? You take that for granted now that you've got these free compilers sitting on your Linux box, and even that OS is free. But at the time, selling a really high quality compiler for $50, that was revolutionary. But of course, he sold a bajillion copies. And then for a good 2 decades, Pascal was the teaching course at universities. Of course, it's since been supplanted, but that's how it went. So this is the Arduino, and there's nothing hugely fancy about it. It's a little microcontroller board. It's got a small, tiny, but fairly powerful little Atmel chip on it. But the Atmel chip isn't really the point of the Arduino. Any of you have played with it. The point is it has a beautiful set of libraries that come with it, and you can get you take it out of the box, and you've got stuff running in about 10 minutes. If you want, you can go deeper, but you don't have to. And then it has this nice little connector that people started building shields for it. The shields are little boards that plug into here on top. They give it more functionality. And it's open source, so there's variations of it. My wife is really into costuming, particularly in places stuff like DragonCon. And she came to me and said, Aaron, I want to get into microcontrollers. And I said, who are you? And what have you done with my wife? But she wanted to start putting various lights and sensors on her costumes. And this is the LilyPad Arduino. It's very pretty, but it's basically an Arduino, and it's designed to actually be sewn into clothing. You can wash it. And there's this whole set of little accessories that can go with it. And this is Leia Buckley. I'm not sure how to pronounce that name. She's a professor at MIT. The LilyPad Arduino is her creation, so here's her wearing those devices. And here is someone, I think that's probably her actually, modeling some clothing made with this device with various things on it. You can see the little Arduino there. It reminds me sort of the discs that everyone has at the back of the Tron movie, which actually made me wonder because they make a big deal about, if you've seen the movie, and this is a repeat of a speech Sarkis in the first one, they make a big deal about this is your identity disc, it's super important, it records everything you know and learn, if you lose it you'll be de-res. But then they take it off and they throw it at people, which if it's super important, should you really be using it as a ranged and melee weapon? It's kind of like me taking my laptop, getting into a bar fight, and then trying to whack people over the head with it or chucking it across the room at them. So, another piece of technology here. 3D printing. These are amazing. You give it a specification of whatever you want to build, and it has some goo, and it plops the goo down and starts building. And some of these are of amazing quality. Now, the point about the MakerBot, what's fun about it as a piece of open source technology, is that when you buy the kit, they give you some temporary cheap parts to build it. Then the first thing you do with it once you get calibrated is you reprint better versions of those parts. So, and you replace the cheap parts with the parts it makes. So it's a device that actually builds part of itself. So it's not fully von Neumann architecture, like in the computer side. It can't actually fully replicate it itself, but there are people working on exactly that. This is Paul Hasler. How many of you know Paul Hasler, professor in our department here? He mostly teaches, I think, upper level graduate classes, so you may not have seen him. He works on analog circuits. Old school op amps, capacitors, resistors. I have a personal love for this kind of old school analog technology. I'll talk about that a little bit more. He's working on field programmable analog arrays, analogous to field programmable gate arrays. And a large part of what he's doing is he's trying to do that Mead-Conway program for this new kind of technology, so that people who aren't experts in analog design, people who haven't taken EC 3050 and stuff like that, can actually sit down, somebody trained in signal processing or some other kind of a field could sit down and design, simulate analog circuits, but without having to get too far down in the details. It's democratizing that kind of technology.